but we'll go ahead and get started. So you already saw some of the questions, but let's go over it real quickly. Oh, you don't have the answers. Let's try to get the answers. So we're going to do the 10 questions, and we'll start over the study guide for the final exam, the last 2 chapters. And then what we'll do is, if you have any questions left over, I'll answer any of your questions. Okay? So number 1, why does fusion take place at very high temperatures? Anybody have a suggestion why that might be? You need high temperatures. Why? Do they want to combine or not really? Not really. They don't really, because they have a repulsive force between them. In order to overcome that repulsive force, they have to be moving fast enough to get really close together. So the answer is to high temperature means high collisional velocities, which can allow protons to overcome their mutual electrical repulsion. Okay? So they don't normally want to get together, but if you slam them together fast enough, they can get close enough that what force takes over? Who knows what that force is called? It's stronger than the repulsive force. It's called the strong nuclear force. You should probably know that. Okay, how did Harlow Shapley, remember that guy? Harlow Shapley. What's his name associated with? There's 2 things now. But anyways, one of them is, how did Harlow Shapley avoid the bias of dust and the stellar distribution when measuring the size and shape of the Milky Way? He actually found a pretty good center. What did he look at? The globular clusters, not the individual stars, right? He looked at the clusters of stars and saw that they made a spherical shape, so that the center of that spherical shape was the center of the Milky Way galaxy. So that was his good deal. Who didn't do that, right? Who were the 2 people before Shapley? You should know their names. The Herschel brother-sister team, Caroline and William. And then after, I forgot his first name, but Kapetyn was his second name. And they both counted stars to get the shape of the Milky Way and looked at the star distribution. But Shapley looked at the globular cluster distribution. Okay, number 3. This is an old question. It's about comets. The ion tail. Okay, so let me stop for a second. Does everybody remember there are 2 tails? 2 tails, right? The ion tail. What's special about the ion tail? It's made of ions, okay, which are charged particles. What's the other tail called? Called the dust tail. And it's made of neutral particles. But the ion tail points directly away from the sun in the direction of the solar wind, right? So whatever answer matches that. What's the answer? In a trailing orbit? No. In the direction of the solar wind? Yep, that's it. In the direction of gas outflowing? No. Directly behind? Not really. No. And so it's straight, right? It points directly away from the sun. Okay. Spring tides, right? Do they only happen in the spring? You're supposed to know that. How often do spring tides happen? Twice a month, right? Twice a month. During the new moon and the full moon. What's happening is the tidal force of the sun and the moon are working together. That should be reviewed. All right, here we go. This is actually, we just studied this, right? As a result of collisions, what is the evolution of galaxies? Is it, you remember that? Spring tides? Yeah. Spring tides are when you get super high highs and super low lows when the sun and the moon together are stretching the earth. They happen at new moon and at full moon, twice a month, every month. The other kind of tide, which apparently isn't on my ask question, but you should know, is neap tide, which is when the sun and the moon work against each other. So the first quarter and the third quarter are the answers to that. Okay, number 5. We just talked about this on Thursday. As a result of collisions, remember, what's his name? Hubble was wrong, right? He thought that ellipticals turned into spirals. He was totally wrong. What's the right way? Spirals collide and will eventually form elliptical galaxies, okay? So ellipticals turn into spirals. That's the evolution. So from ellipticals to spirals. What's the evidence for that? Just to remind you, we're going to go over this in a few minutes. Yeah.
So number 5 is ellipticals to spirals?
Yes, it is.
Oh,
no, I didn't mean it. No.
Yeah.
I said it backwards. Spirals to elliptical. Sorry, absolutely wrong. That's what Hubble said. I'm sorry. It's spirals to ellipticals. What's the evidence to support that point of view? How do we know that that's the right way to do it? If they're new stars, right, then they're young, right? A young galaxy has new stars in it. Do elliptical galaxies have new stars? No new stars at all. They're only old stars. And so the new stars happen in the newer galaxies, in the spiral galaxies. So we know that those are newer and the ellipticals are older. Okay. A comet. Well, another comet question. Wow, that's so funny. But actually it has to do with Kepler's law. So anyway, if you remember, one of Kepler's laws says that the speed of a comet, is it constant or does it change? Does anybody remember? It changes, right? It depends on how you are, where you are in your orbit. So there's a point when you're closest to the sun. What is that point called? The perihelion, when you're closest to the sun. And there's a point when you're furthest from the sun. That's called aphelion. Now, which one is the comet moving faster? Closer to the sun. So the answer is perihelion, right? At perihelion, closest to the sun, the comet is moving fastest. Where does it move slowest? Not that that question is necessarily on there, but at aphelion would be the right answer. Okay, wow, here we go. This is actually from the last exam. What happens when a white dwarf steals enough mass from its companion? What kind of companion? A red giant or, yeah, anyway. I don't think we talked about AGB, right? It's in the book, but anyways, red giant's fine. When it steals enough mass to exceed 1.4 solar masses. Why is that number important? What's it called? Chandrasekhar limit, right? But anyways, what happens? It blows up, right? What kind of explosion? What kind of blow up? I think there's only one there, right? Oh, okay, never mind. It fuses nearly all of its carbon and oxygen. It doesn't say oxygen, but anyway, it's a type 1a supernova, right? Type 1a supernova. So far, so good? How many people feel more confident? This is easy, right? You got this? Okay. Good for you. Okay, that's an old picture. The figure below shows a model of an atom. There are energy levels, right? Remember, the lowest energy level is level 1, closest to the nucleus. Which of the following electron transitions would release a photon with the most energy? You have to remember the difference, right? You can either absorb a photon or release a photon. When do you absorb a photon? When you jump up to a higher level. When do you release a photon? When you jump down, right? From a higher level to a lower level. So the most energy means the biggest jump, right? So we look at it, what are we looking for? From a lower to a higher or from a higher to a lower? To release energy, to release a photon, we want to jump from a higher level down to a lower level. We want the biggest jump possible. So what's the right answer? D, 4 to 1, right? 4 to 1 is the biggest jump. 2 to 1 is also a jump that would release, but a smaller energy photon, right? So bigger jump, bigger energy. Who knows what happens to the frequency of a photon when its energy is greater? A frequency. How does frequency relate to energy? Higher frequency is higher energy. Higher frequency, higher energy. What happens to the wavelength when your frequency is higher? It gets shorter, right? So you have to remember that one of them goes with the energy, that's the frequency, and one of them is exactly the opposite, right? So energy goes up, wavelength gets smaller, but frequency is going up as well, okay? The figure below is an illustration. Oh, I know you recognize it. Okay, maybe not, because you just learned about it, but maybe you can look at the things right here. Recessional velocity and megaparsecs. Megaparsecs. Anybody know who that has to be? It's got to be Hubbles Law. That was Hubbles Law. The further away a galaxy is, the faster it is moving away from us. What are the odds that you'll get another question on Hubbles Law? 100%. So you want to know Hubbles Law, right? You're going to need to know about Hubbles Law. It's not super complicated, but I did ask you to memorize the value for the Hubble constant because it's cute, right? Who knows the value for the Hubble constant? You don't want to say it out loud. Okay. Right. This is a family class, but they won't understand what you're talking about. Okay, so that's okay. We'll go ahead and say it. 69. Thank you very much. Okay. So I know. Don't worry about that. It's a funny number. It's a great number. It has a 6 and it has a 9. Put it together. 69. It's like the Pen Pineapple song. Has anybody heard that? Does he know the Pen Pineapple song? Does he know that one? We should play that just for fun. Never mind, we don't have time for that. Okay. Okay, so how's the Hubble equation work? You don't have to know a lot, but you got to know. The recessional velocity of a galaxy is proportional to how far away that galaxy is. The constant that you need is called the constant of proportionality. To make it an equal is called the Hubble constant. And so this number just happens to be 69 kilometers per second for every megaparsec away that the galaxy is. So if it's one, again, simple questions. If the galaxy is 1 megaparsec away, how fast is it moving away from us? 69 kilometers per second. If it is 10 times as far, 10 megaparsec, then how fast is it moving away? You have to go 10 times 69. That's 690 kilometers per second. Do you understand how it works? It's not difficult. It's just simple proportion. So twice as far, twice as fast. Is there a question like this on your final? Yes, that's why we're reviewing it. Okay, everybody good? So you got the idea. Okay? It might not be 10, it might be 2, it might be 3, it might be 5, but you know the right answer, right? The further you go, the faster it goes. Uh-oh, here, you memorize this fact. Where is the sun in our Milky Way galaxy? Is it at the center? Is it in the halo? Is it in the disk? 1 kiloparsec, or in the disk, 8 kiloparsecs? What's the right answer?
Yeah.
D, 8 kiloparsecs from the center. So a little more than halfway from the center to the edge, right? You might also think about, we learned a little tiny detail. There's names for the arms. Anybody remember a name? The Cygnus arm, right? Or the Perseus arm, right? Are associated with, okay. I'm not going to get into too much. I don't think I actually asked too much about that. All right, everybody good? You got your 10 questions? Are these on the final? Yes, these are on your final already, right? But there's going to be 90 other questions we got to get through. So let's look at our study guide. So our study guide here. Now, I give you guys, since you're here, you get to choose. How many people would like to do chapter 16 first and then chapter 15? Anybody? Nobody? Okay, just go through it. Okay, let's go through it. All right, so you got to know some terms, right? And as we discuss the terms, you want to see if you can connect the ideas as well. And we, again, have already talked about some of these. So what does the term galactic fountain refer to? Can you think of the name? Can you think of a name? You should have a name associated with this term. Bob. Benjamin. You don't have that name. Okay, well, I'm helping you. So Bob Benjamin was a graduate student. I told you the story. And he saw something. What's the galactic fountain refer to? Streams of gas, jets, that seem to be shooting away from the Milky Way. But he also hypothesized that they were going to fall back into the Milky Way. So the fountain idea is that matter can leave one part of the disk and fall into another part of the disk. Why was this important? Because up until then, no one had ever been able to explain how the Milky Way is so well mixed, right? And this is one mechanism. So who read his paper? Spitzer, okay? Spitzer, very famous astrophysicist, right? So very famous astronomer. And Spitzer said, you got a good idea, man. This is awesome. And it explains something that I've been wondering about a long time. So he refereed the paper. Okay, so what's the Milky Way? Our galaxy, our home, right? What do you need to know about the Milky Way? We could draw a quick picture with what you have to know, right? What do you have to know? Anybody? The size. What's the size? Right? So the size of the Milky Way. I'm going to draw a quick little disk picture. Here's the disk. How wide is the disk? 30 kiloparsecs, or 100,000 light years, right? 100,000 light years. That's how big it is. Okay. Now, let's jump a little bit out of order. There's this thing called the halo, right? What's in the halo? There's about 150 of them. What are they? Globular clusters, right? They're in the halo. They make a sphere. How big is the halo? About the same size, right? It's a spherical halo where the globular clusters are located. What else am I missing? I'm missing something. The bulge, right? There's a bulge in the middle. It's about 10 10 kilopar. I'm missing two things. Okay, 10 kiloparsecs across, which works out to be about what? 33,000 light years. About a third of the size of the disk. That seems kind of big, but whatever. Something like that. And then the last thing, what's the thickness of the disk at the edge? Right? At the edge, not in the bulge part. The thickness is 0.6 kiloparsecs. Oops, 0.6 kiloparsecs, which is about 2,000 light years thick. Okay, there you go. That's the basic picture that you have to be able to draw in your head and know those numbers. Okay, I asked you to memorize those numbers. Caroline and William Herschel, we mentioned them before. Brother-sister team, what do? They used Williams telescopes and they counted stars. They measured the distribution of the stars. And what did they find? A flattened disk. Okay, the first people to say, hey, the Milky Way looks like a disk. It looks like it's on its side, right? It's not a circle. It's not a circle, but it's flattened. So it looks like you're looking at it on the edge. But they got the size really badly. So don't even worry too much about that. What was at the center of their Milky Way galaxy? The sun, right? Totally wrong, but we want to understand what was wrong. They got the size wrong. They got the location of the sun completely wrong. And then along comes Jacobus, that's his name, Kapetyn, right? And what did he do? The same thing, but a little bit better. What was better about his technique? There may be a question asking you something like this. He didn't just look at them and draw pictures. What did he do? He took photographs. He used the negatives of the photographs to count the stars very precisely. So instead of having kind of like a hand-drawn picture, he had this beautiful map that he was able to derive. It was the best map that anyone had ever made. And from that, he saw what? It says disk again. But his size was only about 10 kiloparsecs. It was way too small. And again, what was the center of the Milky Way? The sun again, right? So fail, fail. And then who came along to finally show us the right answer? Harlow Shapley, right? And what did he do differently? Instead of counting the stars, he looked at the globular clusters. And turns out he was able to see, they made this big giant sphere. And he says, well, that's perfect. That's beautiful. At the center must be the center of our Milky Way. And so it was a different location than either the Herschels or Kapetyn had found. Okay? So we already mentioned the disk. That's the disk. The disk, the pancake part of the Milky Way. What's important about that? Actually, we're going to get to it in a second. But can you tell me what you think about when you think about the disk? What's special about it? Is there more matter in the disk or in the halo? Which one? What do you think? In the disk. The disk has most of the matter. In fact, that's where all the what? The new stars are forming. All the new stars are in the disk. New stars. You've got material in the disk that can form new stars. Remember the types of material we talked about, right? The molecular clouds, the H1 and H2 regions, right, where you have dense clouds. Then you can make stars. The galactic bulge, what's special about the bulge? It's found where? Right in the middle. And how big is it? We said 10 kiloparsecs, but what's special about the bulge? It has a lot of stars concentrated there. So we mentioned that we threw in some numbers. You don't have to worry about that. Just very dense stars, right? So the space between the stars is small. Probably a fraction of a light year is the average distance between the stars, like 0.1 light years instead of 4 light years or even more. Okay. So what about the stellar halo, or galactic halo it's also called? What's special about that? What do you find in the halo? The globular clusters. Okay, that's where the globular clusters are located. Okay. Spiral galaxy, what does that mean? It's got arms, right? And I actually don't think I did too much, did I? I didn't do it. See, I may have a little word down there. We talked about the spiral density wave, but the idea is that some of the arms are very well defined. They have stars all the way along their length. Those were called the grand design spiral. And then there was others where there's gaps in between. And the reason is that the stars don't form all at once. They propagate down the arm like a sound wave almost, right? A little by little by little by little along the arm. And so those were called flocculent, right? Flocculent spiral. I don't know that you have to know that, but whatever. Okay, so let's see. How about the word, again, spiral arms we mentioned. They're just arms. What are the spiral arms actually? Are they the stars? They're the matter that hasn't yet actually formed stars, so it's dark. But the edges of that dark material are going to be stars, right? We'll see new stars at the edge of that material. What's the term metallicity? Anybody? The amount of metal, right? So amount of metal. So when you talk about metallicity, you think about generations of stars. So which generation doesn't have any metal? First generation, right? You start off, all you've got is hydrogen and helium. And then each generation enriches the next generation, and you get a higher metallicity. So the newer the star, the more metal content it has. So where do you find new stars? In the disk. So where do you find metal-rich stars? In the disk. What do we call those stars in the disk? Population 1. So you're supposed to connect a bunch of things. Population 1 stars are stars that are found in the disk. Are they high or low metal content? They're high metal content. They're newer stars. They're also newer stars. Sorry, that's the third thing. They're also newer stars, right? What about population 2? What's that mean? Old stars found where? In the halo. And what generation? Probably mostly first generation stars. So very metal rich or metal poor? Metal poor. There's almost no metal. Okay. All right, population 1, population 2. Okay, barred spiral galaxy. What does that mean? Want me to draw a picture, or you remember? It has a stretched out center. Instead of a very strong circular center, it's stretched out. It makes a little bar, and the spirals come out of the ends of the bar. How do you make something like that? I told you one possible answer from tidal forces. Another galaxy stretches it and causes the center to be elongated. And that's actually, keep that. That's the best thing you're going to hear in this class, okay? So if you take a more advanced class, you can learn. There's some other mechanisms maybe. But for now, that's what we're going to say is the best answer. All right? Andromeda, local group. What's that? Local group. The local group is the local galaxies, right? The galaxies that are close to us. And because they're close to us, what does it mean? They are connected to us by what force? Gravity. Are they ever going to leave us? They're never going to leave. They're always going to be close to us. In fact, one of them is coming to join us. What galaxy is coming to join us? The Andromeda galaxy. So a couple of things about Andromeda. Andromeda is special. Remember why? Anybody remember why? We're going to come up to it in the next chapter, but maybe you could just remind me if you remember anything. It's the closest spiral galaxy. How far away is it? You should have some idea. Is it 100,000 light years away? No, that's the size of the Milky Way. How far away is it? I know somebody knows. 2.5 million light years away. It's nowhere near the Milky Way, right? It's really big distance compared to the size of the Milky Way. But it's coming to join us. I don't know if I mentioned it. Probably has about 1 trillion stars. I don't think you have to know that. But anyway, a little bit more stars than we have. But you do need to know, well, that's in the next chapter. All right, I'll talk about it later. Okay, large and small Magellanic clouds. Actually, that should be in the next chapter too, isn't it? All right, well, what are they? What are they? Bless you. What is that? Remember what they're called? They're orbiting the Milky Way, and they're in the process of being eaten. What are they called? They're dwarf, and they're actually, we give them, I was saying that they were elliptical, but we now know they're not elliptical. They used to be called elliptical. What do we call them now? Irregular. And what makes them irregular? There's giant streams of matter that are actually being dumped onto the Milky Way. We call them the Magellanic streams. And that's the Milky Way eating them. What is the mechanism by which the Milky Way is eating them? Gravity. The tidal force of gravity is ripping them apart, right? So our galaxy is doing that to these little tiny galaxies which are nearby. So does anybody remember the sizes of these dwarf galaxies? So I should have said something else. There's another thing to remember. How much mass is there in the Milky Way? This is our Milky Way, right? Milky Way, how many? 10 to the 11th solar masses, right? 100 billion solar masses. How many stars? Oh, I forgot to mention that. What's the right number? About what? 400 billion. I know the numbers are bigger, but now we have billionaires in the world, so now you can start thinking about that. They should just give me one, and I can handle it for my life. All right. 1 billion for me, 1 billion for you, 1 billion for you, 1 billion for you. We'd all be cool, right? What would you do with $1 billion? It's not relevant. Okay. All right. Oh, I did put it in there. Okay. All right. So what's an O and B association? Anybody know what they're talking about? O and B association. O and B stars are found where? At the edges of the spiral arms, right? So if you look for those O and B stars, then you can see where the edge of the dark material must be. Is there a way to directly detect the dark, undeveloped material of the spiral arm? You need to know the right answer. The answer is, of course there is. What is the right technique for detecting the cool, neutral, hydrogen gases that are in the dark parts of the spiral arms? Nobody remembers. Come on, somebody. Cold. H1 regions. Come on, how do you detect H1 regions? You know, radio wave. Radio, right? They shine in the radio part of the electromagnetic spectrum. They're cool, but they shine in the radio part of the spectrum. So radio astronomy can see them, and they're right next to where the O and B stars are forming. So that's a really good way for us to check that. Okay, so Sagittarius arm. Sagittarius A. Spiral density wave. We need to do that. What does that mean? Does the matter spew out of the Milky Way and move towards the outside? Does the matter move out? No. The shock wave moves out. And that's what we're calling the spiral density wave. Along each spiral arm, the shock wave, little by little, moves. And that's called a spiral density wave. Everywhere it compresses the matter, what happens? New stars are born, right? So you get a wave of new stars being born, and it moves gradually down the arm. It takes a while. It takes a long while, right? Not a human lifetime, many, millions of years. Actually, I just thought of one more tiny little detail. Does everybody remember that the Milky Way, the sun is right about here, right? 8 kiloparsecs from the center. Here's our sun. And it's orbiting the center of it's orbiting the galaxy, right? How long does that orbital period last? How long does it take? Anybody remember that? The sun, orbital period in the Milky Way, right? In the Milky Way, Milky Way. Anybody remember? About 233 million years, right? So every 233 million years or so, right? The sun has gone once around the Milky Way. All right, keep thinking of more stuff. Okay, Vera Rubin. Why is she important? I put her name because I want you to know her name. She's really important. She was the first person to start looking at something. The rotation curves of what? Galaxies, right? And she discovered something disturbing. Does anybody remember what she discovered? The predicted speeds don't match the observed speed. So the picture was, the blue pen is fading. Okay, the picture was your velocity of the star versus the radius or distance from the center. And I guess we could go light years or parsecs, whatever. Kilometers per second, or something like that. And what they expected was that it would show something like this. That was the expected. And what was the real? The actual. Yeah, it was like, even like a little bit higher. Almost the same, but a little bit higher. That was the real, the actual. And so, did anybody expect that? No, nobody expected that. And she was the first person to say, hey, we didn't expect that. Right? We didn't expect that. We expected this because we thought that the bulk of the matter was in the center. That's what we thought. But she found this, and suddenly that doesn't work anymore. And so what is Vera Rubin credited with coming up with? The concept of dark matter. Dark matter. The only way that this could happen is there's a lot of extra matter here. So this halo is actually probably where most of the dark matter is. Right? Some of it's in the disk, some of it's going through us right now, but most of it is out here in the halo. And what percentage of the Milky Way is dark matter? 90%. This is kind of disturbing, but you need to know that percentage. Can we see the dark matter? Do we know what it is? No. Does that bother you? It bothers me, by the way. It doesn't have to bother you because you're not an astrophysicist, maybe, but it should bother you that we only know about the stuff that we can see, right? So this is the light matter. What does light matter mean? It's emitting light, right? So we can see it somehow. So there's 10% of the matter that we can see, but 90% we can't. And that was the only way she could get these kinds of speeds, right? Otherwise, it didn't seem to work. So what's the right explanation? There's matter out there that we don't know. We're not sure what it is. But we had a couple of ideas, and one of them is definitely a possibility, and the other one has been ruled out. You should know which is which. So we got the word macho and whim, right? Macho. What does macho stand for? Massive, M-A, compact, H, halo object. Great. Massive, compact, halo object. And what was a perfect, massive, compact halo object? A black hole. So we thought, hey, it was really, people were so excited. This is going to be, that's the answer. There's just lots and lots of black holes. But it turns out we couldn't see the little flashes of light that should have been there, this gravitational lensing effect. So macho would have been a bunch of black holes, and they don't have accretion disks, so we can't see them because they don't shine with light, but they have a lot of mass and they're really small. That would have been perfect, but the experiments to see them didn't see the effect that they would have seen. And so this one is no longer considered an option. You should throw that one away. It's there, but we now know it's not really the right answer. And now we're stuck with WIMP, okay? So we've got nothing but a WIMP to save us. These WIMPs can save you. Never mind. All right. It's not that funny. Am I any funnier on recording? Is this funny? No. All right. I'm recording. It's not live stream. I'm so sorry. All right, whatever. I can't do it. Shoot. All right. WIMP. What's a WIMP? Weakly interacting but massive particle, right? Weakly interacting massive particle. Are neutrinos part of the WIMPs? I don't know that I mentioned this enough. Are neutrinos a possibility for part of the WIMP? Yeah, a little tiny piece. Maybe like 5% of the WIMPs could be neutrinos. Remember neutrinos? They're very weird. They go through the Earth, right, without stopping. That's a good example of a weakly interacting particle. It just doesn't stop. It doesn't stop for the Earth. It doesn't stop for the sun, right? Nothing stops it. That's the kind of idea. These particles just don't get stopped by anything. So they're there. We know they're there because sometimes they do get stopped. So if we could design an experiment to detect this weakly interacting matter, then that would be pretty cool. And it could change everything, right? We would suddenly understand more. So what is it? What's the weakly interacting mean? We're talking about something. What are we talking about? The weak nuclear force. Okay? So again, if you don't know what that is, you should write down just, like one quick sentence. What is the weak nuclear force responsible for? And I would say the best answer is something like, you got one? The stability of a proton or neutron. It's actually, maybe you could say, holding together a single proton or a single neutron. The force which keeps it together. It is actually connected with that. Okay? But I like the stability thing, but whatever. Something like that. Okay, so I actually talked about a lot of these ideas, so let's see how we do. Describe Bob Benjamin's interaction with Lyman Spitzer. Who was who? What's Bob Benjamin? Grad student. Lyman Spitzer. Referee. Reading his paper. About what? It says right there. Galactic fountains, right? And did he like it or not? He loved it. It was a great idea. And so he was super excited. to see the evidence and actually, in fact, help them later on in life. As a matter of fact, to develop that idea. Okay, so blah, blah, blah. Okay, so is that okay? What does it do? It shoots. Oh, I didn't talk about how it shoots the matter out, right? You need to know that. What's the mechanism by which these jets escape, or don't really escape, but get away from the disk for a little while? How do they get away for a little while before falling back? Supernovas, right? Supernova blasts shoot the material away from the disk, but eventually they fall back into the disk. What pulls them back? Gravity. It's gravity. Always gravity, right? Gravity pulls things together. There was that little tiny idea as well associated. Remember that stars that are a little bit above the disk, they get pulled toward the disk too. And when they hit the disk, do they hit anything? They don't hit anything. So what happens is they go past the disk, and then they end up oscillating back and forth, right? And actually we think quite a few stars do this. But they don't go very far from the disk. They just oscillate up and down. Maybe our sun is even doing this a little bit. Okay, we actually talked about, we already talked about this. Who are the people that you want to talk about when talking about how the model of the Milky Way has changed? Who are the first set? There's two people. Caroline and William Herschel, right? They did the first model of the entire Milky Way. It wasn't very good. The sun was at the center. It was a little disk. It just wasn't right. And then later we had Jacobus Kapetyn. Did a little bit better, more detailed math, but again, the sun was at the center. It was still a pretty small disk. And then finally we had Shapley, right? And Harlow figured out that the globular clusters were the key. If you watch them, instead of watching the individual stars, you get a much better picture of what the shape of the Milky Way looks like, okay? And we figured out where the location. All right, so I don't know. That question is kind of like just in there, but I just went over that, right? Did I kind of talk about that? Explain how the Milky Way center was able to be located by using globular clusters, but not when you're using stellar distribution. Anybody know what was the biggest problem for the Herschels and Kapetyn when they were counting stars? They couldn't see all the stars, right? The dust blocked their vision. And so because of that, the picture that they had was not complete. And so they couldn't do a very good job. I mean, they did the best they could, but it just was incomplete. And Shapley, because where are the globular clusters located? In the halo. Are they in the disk? No, they're in the halo. Do they get blocked by dust? No, they're in the halo, right? So because of that, he had a clear shot at seeing where they were located. See the difference, right? So the things in the disk can be obscured because that's where the dust and the gas clouds are. But in the halo, we're pretty good. What's population 1 and population 2? I think I hit that a couple times. Population 1, where are they found? In the disk. What's special about them? High or low metallicity? High. Young or old? Young. Population 2, where are they found? In the halo. Young or old? Metallicity? Low. You got it. That's it. Describe the interactions between galaxies in the local group. Okay, so what's a Magellanica stream? Oh, the Magellanic tidal stream. It says it right there, right? It's tidal force from what? From the Milky Way on these little tiny galaxies. And it's being ripped apart by the tidal force of the Milky Way. And we can see that. And what? Oh, I put it here. Okay. When is this going to happen? 4 billion to about 8 billion. By the time it's done, did I mention what's okay, future collision. We're going to collide, right? Because I put it here. What's the name of the galaxy? The Milky galaxy. It's not a huge fact, but since I told you, I want you to know it. Okay? There could be a question asking you the name of the future galaxy that forms when Andromeda and Milky Way merge, right? That's a nice, easy question. And all you have to do is know the right answer. And I'm going to put something stupid like Andro Way, right? The Andro Way galaxy. And people didn't come to the review or didn't pay attention. They won't know what the heck is wrong, but they won't get that one. You know the right answer. Right answer is? Milkomeda. Okay, great. Yeah, take a cookie. You got some candy, too? Just gotta help yourself. Did you sign in? Okay, so how do we see the spiral arms? I feel like I already covered that. You want to, somebody tell me? How do you see the actual arm? The dark part, the matter that hasn't yet born stars, right? What is it? How do you see it? Radio waves, right? The radio is going to give you an indication of where it's located. You'll see from the 21 centimeter line, you'll see branches of this dark matter. But at the edge of that, what will you find? The new stars, the O and the B class stars. Why do we pick O and B over other classifications? They're young, right? We know they're young because they only live for a little while. So if we can see them, they're young, right? They could, the biggest ones only live 100,000 years. So if we see them, we know that star is really pretty young. Okay? All right. I feel like I've done all of this. I got that right? Got Vera Rubin? Everybody confident? Vera Rubin, what'd she look at? The rotation curve of galaxies and found out that they go too fast, right? Especially when you go away from the center. And so there must be dark matter. How much? 90% of the matter must be dark. How come machos are not considered a good candidate anymore? We didn't see the effect that we expected to see, which would be flashes of light from gravitational lensing. I throw that in there because that is a cool little fact. It's not a huge deal. But we didn't see the flashes when we looked for them. We saw one or two, but we should have seen them all over the place. Right? We didn't see them. Okay. How will WIMPs interact with matter? Do they interact through the gravitational force? WIMPs. That's the whole point. Yes, they must. Because they're making things able to go faster near the edge of the galaxy. Do they interact with the electromagnetic force, aka light? They do not. You can't see them, right? They don't interact with light. Do they interact with the weak nuclear force? They may. We hope they do, right? If they don't, then we're in trouble. But they probably do. Okay? It's just very weak. You don't see it. And so that's probably going to be it. And the strong nuclear force as well, though I left that one out. Just call it weak. Probably not so much of that strong nuclear force. Okay. How is galaxy formation similar to solar system formation? What's similar about it? Anybody? Big cloud becomes smaller. What happens? It rotates faster. Ooh, that's a similarity. That's something you should know is similar. What's the concept that tells you that it has to rotate faster? Conservation of angular momentum. Good job. That's great. If you really see that, then you have really learned something important because it's everywhere. Everywhere you look, whether you're forming an individual planet, a star, or even a galaxy. Conservation of angular momentum is a law of physics that is there. It works for anything, no matter the scale. Okay? What's different about a galaxy from a solar system? One difference, really important difference. Okay, Vera Rubin was the one who first revealed this difference, to be honest. Where's the matter located in a solar system? In the star. How much of it? 99.86 or whatever, 99+% is in the star. In a galaxy, is that true? Not at all. Unfortunately not. We have this giant halo, and that's where 90% of the matter is. So it's really different, right? Can you guys understand the difference there? So we have the bulge where you do have more mass, but it turns out most of the mass, and we might be wrong about this, by the way. If you read an article that says, oh, I've got a model that doesn't need dark matter, they come out every year, several a year. People are trying their hardest to come up with a model that doesn't require dark matter. Why? Because we can't see dark matter. You don't like to put things in your theory if you can't see them. That's not science, right? You've got to be able to detect it somehow. So people are disturbed by this. So they're trying different things, but no one has successfully presented a model that doesn't require this extra matter. Okay, memorize. I think I've already got everything. Huh? Okay, so we are actually located on the Orion Cygnus arm, which is 8 kiloparsecs from the center. Oh, the center of the Milky Way. We have, what do we have? Supermassive black hole called Sagittarius A. I guess that was on the list. I forgot to mention it. How do we know it's there? Does it have an accretion disk? Not most of the time, actually. In fact, most of the time the answer is 0. No accretion disk. Can we see it then most of the time? Not most of the time, but there is some evidence that it's there. And what is that evidence? What's the most direct evidence that we have? The stars that are orbiting this invisible spot, right? But once in a while it does flare up. It's not that it doesn't flare up, it does flare up once in a while, and it has radio waves coming from it as well. We didn't describe that too much. Do you need an explanation? Anybody want an explanation? Actually, I would love to talk about it, but it's not going to be a big part of your test. Anybody want to know, though? Yeah? Oh, good. Thank you. Just a 1-minute explanation, okay? So it turns out that this black hole it doesn't have an accretion disk. But you remember they talked about these very high temperature disks like coronal gases? There are some coronal gases there. So there's probably some kind of a circulation pattern going on, but it's not very strong. An accretion disk would be a strong circulation. But there's going to be some kind of circulation of charged particles near the black hole because of its presence, right? They're going to be forced into a ring or some kind of a motion like that. Because they are charged particles moving in a circular path, they will generate something. What is that something? A magnetic field, right? Black holes, when they have accretion disks, have giant magnetic fields. We didn't cover this. I'm going to cover it in chapter 16 stuff because you should probably know that. When they have the accretion disk, there's a lot of material circulating. The magnetic fields are crazy. They're super powerful. But when they're not very much magnetic material, then the magnetic field is not nearly as strong, right? You've got magnetic field, right? Magnetic field. All right, now, you're a charged particle, and you hit a magnetic field. What do? You spiral, right? That's what you do. You spiral. A charged particle comes in, and it spirals, right? But because the magnetic field is weak, right, there's a problem. It can't actually trap particles that are moving too fast or have too much mass. It can only trap the very small mass, not too fast particles, right? So it's weak. It only traps, and we say traps because it's not really a trap exactly, but they're going to circle for a while. It traps low mass, slow particles. Slower. They're still pretty fast. Okay, so these are slower electrons. And because they're slower, they circle it at a slower rate. The frequency of their oscillations is in the radio part of the spectrum. Okay? So what kind of waves do you get from this? This weak magnetic field, you get radio waves. So you might remember that we said that it's a source of radio waves. Well, that's what they're coming from. Now, what happens when a black hole is more powerful? It has a big accretion disk. We'll talk about this in a few minutes. You get a really powerful magnetic field. What does it mean? You can trap massive, high-velocity particles, which can oscillate at a really high frequency, which means what will they generate? They'll generate X-rays, photons, right? So the energy of the photons that are produced is called synchrotron radiation. Changes depending on the strength of the magnetic field. I went into way too much detail. You don't need all of that. But you can hear me, and maybe it makes sense, and hopefully that's enough. And there aren't going to be many questions on this kind of topic, but there is one question in the next chapter where you should think about that. Okay, so the mass I put 4 is about 4.1, but 4 million solar masses is the mass of planetary thing. Percentage of dark matter, we got that. Luminous, what does that mean? Light matter, right? You can see it. It's shining with some kind of light, any kind of light, visible or otherwise. Radio is okay too, right? Any kind of light. All right, so that's chapter 15. Everybody okay? Yeah. Not that bad? Are we doing okay for time? How are we doing? Oh, we're doing great. I told you, no problem. No problem. Okay, chapter 16. So, oh, there it is. Okay, I did put it in there. I forgot. All right, so what's a spiral nebula? What are they talking about? Do we have spiral nebulas anymore? No, it was the old name, pre-1930s, before pre-Hubble, for what? were spiral galaxies, but they didn't know at the time that they were spiral galaxies. We're talking about the Great Debate, right? The Great Debate, which was, what's the nature of the universe? Is it just one thing, or is it a whole bunch of things? Is it one galaxy? The Milky Way is everything? Or are those little spiral nebulas full galaxies of their own? And we know the right answer. Yes, of course they are, right? Every spiral nebula is another galaxy with billions of stars in it. And I showed you a little video clip. Even in the darkest part of space, when you stare long enough with a good telescope like the Hubble, you find thousands of galaxies that we can't even see. It looks black, right? It looks totally black, but nothing is black. So that's a pretty exciting thing. Okay, so spiral nebula was actually going to be a spiral galaxy, but before the Great Debate, before Hubble, we didn't know that. Okay, so what's a grand design spiral? Spiral galaxy, how do you define it? Well-defined arms, completely continuous, right? There's no breaks in the arm. So stars all the way along the arm. Okay, a flocculent spiral, it seems to be having a little trouble, right? It has gaps along the way. And it might be a newer spiral. Maybe that's one of the reasons. You don't have to worry about that. But it could be part of the age thing. It could be, or even a later stage, actually, when it's running out of fuel. There might be different reasons. You don't have to worry about that. But you see something where the arms are incomplete. I don't think you're going to have to worry about that too much, but it's in there. What's a barred spiral? Instead of a nice compact center, it's stretched out. What's an elliptical galaxy? Anybody?
Egg-shape.
Egg-shape, right. Egg-shape or oblong, right? Sphere, it could be sphere, or a stretched out sphere. One or the other, something like that. Irregular, I put CD. Okay, you don't really have to know. Okay, I lied. You don't have to know this and this. CD, forget about that. And lenticular, don't worry about it. Okay, I put them on there and then I changed my mind later. Sorry about that. I should have taken them off. But you do need to know irregular. What's irregular? What does it look like? Spiral or elliptical? Neither. What does it look like? A mess. Yeah, it's a mess. And what's one good reason why it might be a mess? Galaxies colliding. It's in the process of colliding. That would be a great explanation. If you get that idea, there's a reason why it doesn't look very good, and it's in the middle of a big mess. Okay. What was the Hubble tuning fork diagram? Anybody remember what that was? It had a diagram, and then it split into two branches. You don't have to know a lot, but again, what was Hubble thinking? He thought which one was the youngest kind of galaxy? Elliptical galaxies were the youngest. And when they started, what did they look like? The youngest galaxy. I'll give you the quick rundown, right? I got this movie. All right. The youngest ones were actually spherical. He calls them E0, right? And then what happened? They slowly got a little more elliptical. And then eventually, you got, I went too far. Let's stop right here. Eventually, you get a spiral. He called it S0. Okay? That was the first spiral guy. So they evolved into spiral. That was what Hubble thought. And then there were two branches, right? What were the two branches? The regular spiral, right, where you have the arms coming out. And you might have flocculent spirals until you finally get the grand design spiral. And then you have the other branch. What was that? The barred spiral. So you had the bar with the arms coming out of the end of the bar. Okay? So the S1 and SB1. You didn't have to know, but whatever. There were two branches that Hubble thought. Okay? Was he right? No, totally wrong. Right? So, all right. Megaparsec. What's a megaparsec? Easy. Mega means what? Million. 1 million parsecs. What's a parsec? 3.26 light years, right? Hopefully you remember that. You should have some idea what it is. A parsec is an angular measurement, right? What does parsec mean? Just to review, I don't know if anybody remembers that. A parallax angle of 1 second. Remember that? Parsec. Okay. That's what it is. Okay, megaparsec. Edwin Hubble. What did Edwin Hubble do? Special. Something special. So actually, we throw his name in here, but we're about to talk about the great debate. How did Edwin Hubble settle the great debate? That's actually what you need to know. Edwin Hubble settled the great debate by looking at what? The Andromeda spiral nebula. And he got lucky. You need to know how he got lucky. What did he see? He was actually had a really beautiful telescope, and he was able to see individual stars in Andromeda, and he found some of these Cepheid variables. Okay, if you didn't think of that right away, please write it down. That's the important idea. Why is finding a Cepheid variable so cool? He got lucky. If he hadn't found them, I'm not sure we would know by now. Well, we probably would. But what was special about the Cepheid variable? What's special? There's a connection. What do you know? Luminosity and period, right, are connected. The luminosity and the period are connected. The longer the period, that's the time it takes to repeat, right? It's a variable star. It gets brighter and dimmer, right? Brighter and dimmer. It has a period. The longer the period, the greater the luminosity. Okay? So you're supposed to know that relationship. Okay. Anyway, Cepheid variable. Okay. Calibration, cosmic distance ladder. You guys know what that means? Calibration, what does that mean? Hubble is also famous for something else. What else is he famous for before I go on? The equation we talked about, right? The Hubble equation. That's another thing that he's famous for. Okay, calibration. What does it mean? To calibrate. You're taking steps on a ladder. Which step do you take first? The first step. Okay, what about the next one? Then you take the second step, right? But in order to take the second step, what do you need to do? That's the word. Calibrate. What does that word mean? How do you calibrate? What do you do? Compare, right? You have to be able to see a star using both techniques. You have to use both of the techniques. And you have to say, hey, it's the same star. I know that distance using technique 1. But now that I know that distance from technique 1, I can calibrate the second technique to match that distance. That's calibration. So what happens if later on, I'm prepping you for a question on your final exam, but hopefully you're listening. Right? What happens if later on you get some new information and your first measurement was wrong? What do you have to do? You have to recalibrate. You got to go back and redo each one of the steps again. Is this going to happen in the future? It is going to happen many times, right? Every time we get better technology, we're going to get better distances for that first rung. What is the first rung of the ladder? Which technique do we use? You got to know it. Sorry, if you don't know this, I'm really disappointed. Come on, you know it. The first technique that was used is called stellar parallax. Very good. You knew it. Who knew that? You knew that. Come on, you got to know. Stellar parallax. How do you do stellar parallax? What do? You ride the Earth and you take pictures of the stars. How do you do it? Take a picture. Wait 6 months until you're on the other side of the orbit. Take it again and see how it shifted in space. Bam, you can figure out how far away it is. So why is it that this is going to get better? Can anybody give me a reason why we know that stellar parallax is going to get better? What makes it better? We can take better pictures. Okay, better resolution. Okay, that's actually not the biggest reason. That is a good reason. That will improve something. But that's not the biggest reason. There's a really important reason that I think you're supposed to know because I told you, but maybe you forgot. How do you get better precision? You know the answer. You don't know? Not sure? No. What is it?
When the telescopes are in space and not
What is it?
when the telescopes are in space and not
Okay, why is it, well, we already do it in space. What is it though? Not just in space. Yes, that's good, but there's something else. Okay. The what? The baseline. Yes, that's it. Okay. The further apart your pictures, the more precise your angular measurement becomes. So right now we're kind of stuck on Earth, right? We got satellites going around at Earth radius. But what happens when we get them at Jupiter? They're 5 times as far. we get even better precision. So I guarantee every step on the rung every rung on the ladder is going to be recalibrated. But that's a good thing, right? It's just going to get better and better as time goes on. And then maybe, we're going to go to another star. Well, that doesn't work. Oh, yeah. We can take pictures of the other star in here. Oh, that would be amazing. You guys know what that would mean? Look out, universe. We're headed out there. By then we have warp drive, right? We can do it. Okay. I'm off on a tangent. Sorry about that. All right, let's go. What about, okay, so the steps. You need to know the steps. Does anybody remember this? The first step we just said was parallax. I gave you a second step. It's there. Oh, it's right there. They're listed for you, but you got to memorize the order. Okay? You don't have to know exactly how far they go, but you're supposed to know the order of them. So the first one was parallax. The second one, spectroscopic parallax, which is really about matching the spectrum of different stars, right? And if you know that the spectrum is the same, then it is in fact the same star, it has the same luminosity, and therefore you can calculate the absolute magnitude. The next step. Cepheid variable. Yeah, Cepheid variable, that's right. And that one's good for millions of megaparsecs, right? It's good for megaparsec. And then this one, not so great, 15 megaparsecs, but you don't have to know those. Never mind, you don't have to know that. Next one, Tully-Fisher. Do I like that one? No, I don't like it. But it's supposed to do what? What are you supposed to do? Look at the rotation curve of a galaxy, and you will be able to estimate the mass of the galaxy and the luminosity of the galaxy from the rotation velocity. It's not very good. And in fact, we could almost skip it. Okay? And then we get a really good technique. This is super good. What is it? What was that? Oh, sure. Okay. So the Tully-Fisher, we don't like this one so much. The reason we don't like it is very inaccurate. But what it does is we look at the rotation curves of galaxies, and from that we have a model that tells us the mass of the galaxy, and therefore the luminosity of the galaxy. So that's kind of remember the idea of a standard candle. If you know the luminosity, then you know the absolute magnitude. There's two questions at least on this idea. How do you use absolute magnitude to find the distance to an object? What do you compare it to? The apparent magnitude. Hopefully you got that idea, but that's the standard candle method, right? If you know the absolute magnitude, you compare it to the apparent magnitude, and then you know how far away it is, right? So the brightness of something, as you see it, compared to what it should be, the apparent magnitude. I forgot. Anybody remember what absolute magnitude means? The apparent magnitude when the object is located at 10 parsecs. Very good. Good for you. Okay, so the next one, really good, is type 1a. This one is probably, other than Hubble, the best, right? But Hubble is also really good. So these last two are exceptionally good. We're finding out how good they are. They seem to be incredibly precise at measuring very big distances. Okay? So type 1a supernova, what's happening? A white dwarf with a red giant companion. Sucks matter. Every time it does, what do you get? A flash of light called a nova, right? That doesn't blow it up, right? The nova keeps happening. A little flash. But every time it does, it leaves a little bit of matter on the white dwarf. Eventually, you go over the limit called the Chandrasekhar limit, 1.4 solar masses. Did anybody go look up the real number? No? Okay, it's actually a little tiny bit higher, but we didn't say that. All right, never mind. Nobody did. You could have corrected me, but it's not. We're friends. Okay. But 1.4 solar masses is the number we say. And then it blows up. And that supernova is all at once fusing the carbon and oxygen that are left in a white dwarf, right? Okay, Hubble's Law, super powerful. We did talk about it right here. Memorize the number 69. That's the kilometers per second per megaparsec. So again, very simple to use this formula. The bigger the distance, the faster the galaxy is moving away from us. If you go twice as far, the galaxy must be moving away twice as fast. Now, it doesn't count which galaxies. This doesn't work for which galaxy. It doesn't work. The local group. It doesn't work. We're not talking about the local group. Those are the local, those are our homies, right? They live with us. I was trying to be funny, it didn't work. Okay. Okay, that one. Okay, but anyway, the local group is just that the handful of galaxies that are close to it. The Hubble Law doesn't apply. It only applies to further galaxies, okay? Hubble constant, I already told you, we know the number. Active galactic, oh, we didn't talk about this at all in class. Okay, so there are some galaxies out there that are super exciting. And when I say exciting, I mean that they routinely emit 1 billion times the amount of light in our sun. 1 billion times, and they keep doing this over, I mean, for an extended amount of time. We've had different names for them, and you could read more in the book if you want. I'm not going to ask you a lot of questions. There might be just like one. Although I think I do ask you the meaning of quasar, so I'll throw it in there. We'll talk about these terms. Active galactic nuclei is the idea that at the center of every galaxy is a, just like ours, super massive black hole. Okay, so now let's try a little bit more. How do you get active? What's important for active? Okay, yes?
Absorbing material.
Not absorbing. Oh, yeah, sorry, yeah, I see what you're saying, yeah. It's actually not necessarily absorbing material, but having an accretion disk of some kind. And that's what I think you're saying, right? Yes, you're right, that's good. But in fact, one thing that's active is a powerful, what about it over there? Magnetic field. Active galactic nuclei are supermassive black holes with extremely powerful, like the number, it's just, how many stars in the universe, that kind of thing. It's just really powerful magnetic field, beyond all comprehension. They're not like stars. They're just billions of times more powerful. It's just incredibly powerful. Question?
Is not every black hole's active?
That's right.
What makes it that?
Okay, so you didn't hear the answer?
No.
Having material falling in,
Okay.
having an accretion disk, or a lot of material nearby that is circulating. The more material that circulates, can anybody tell me? The more circulating hot plasma material, the stronger the magnetic field. It's super easy. I mean, we're not going more complex than that. So the more material, the stronger the magnetic field. So particles that come in and hit that magnetic field, they go whoosh, right? And they do that. What do? They get shot away. Okay, I'm going to tell you a little bit more. They get shot away from that active galactic nuclei in these things called jets. Jets, right? They're in both directions. Jets. What's a jet? It's evidence of an active galactic nuclei. What causes the jets? Magnetic field. How exactly? I have no idea. Now I kind of have a little tiny idea. But the idea is, I'm not going to get into any detail. Here's what happened. A particle comes in and is moving near the speed of light and hits that magnetic field. It's super powerful, and it goes spiral, pow! Bam! At the speed of light. Not quite. Almost. Now there's something super freaky. You want to hear something super freaky? Yeah, I'm about to sing. No, I'm just kidding. Yeah, super freaky. We actually have measured the particles moving faster than the speed of light. How many people have a problem with that? You should, according to what theory of relativity? Special theory of relativity. No particle of mass can move faster than the speed of light. Not allowed. It turns out it's probably just a mistake. It's not really moving faster than the speed of light, but it seems to be. And what it means is that jet is pointed towards us and is moving like at 99.9999% of the speed of light. It's almost moving at the speed of light. So we see they're called superluminal. That's the word superluminal. What does that word mean? I just defined it for you. It appears to be moving faster than the speed of light. Okay, so what's a safer galaxy? So there's actually two types, and it has to do with the speeds of the particles that are emerging. So there's type 1 and type 2, low velocity and high velocity. And let me see, what's the connection? So the idea is active galactic nuclei is a galaxy which is spewing radiation and particles in these jets. We have lots of beautiful examples. A Seyfert galaxy is a radio galaxy that also is spewing particles, either a low velocity type 1 or high velocity type 2. You don't actually need to know that. And then we have the word quasar. So before we understood what those were, we have the name. Let's just break down the name. What is, anybody know what quasar stands for? Quasar. Okay, quasar. We don't use the term quasar anymore. It's actually all going to be the unified HEN model, but that's okay. Right now, quasar, I want you to know the word. Quasi-stellar radio source. Okay, so what happened was we discovered these galaxies that were emitting an amazing amount of energy, but were incredibly far away. And actually, that's how we found out they were emitting a huge amount. They were bright, even though they were incredibly far away. And therefore, they must be emitting an amount of energy that we've never heard of before. And so we think that the quasars are really just, and these as well, all of these are really part of this, the unified AGN, unified active galactic nuclei. Okay? And when I say outflow, anybody want to guess what that means? What am I talking about? Outflows. Jets, right? Okay, so actually I explained just a tiny little bit. That's all you really need to know. What causes the outflows in these active galactic nuclei? What causes them? Without this, you won't get outflows, which is why not all galaxies have them. No, it's super easy. Magnetic field, right? Magnetic field. If they don't have a magnetic field, they don't have jets. They don't have flow. Okay? So then, how do you get the jets? You got to have a magnetic field. How do you get the magnetic field? You've got to have material feeding the supermassive black hole at the core of the galaxy. Okay, so the unified AGN model has a few features. You can read more about it in your book. But it's just like, what does it look like? That's all it is. It's a description of what might make these beautiful things. Okay? So what's in the center? Supermassive black hole. SMB. Supermassive black hole. Is it a bare supermassive black hole? Is it all by itself? That would give you nothing. You wouldn't see it. It would be boring, right? How do you make it active? You need a magnetic field. How do you get a magnetic field? Got to have material. So it has multiple features. It has a ring of material that is falling in. It's a pretty big ring. But what is that ring called? An accretion disk. Now, it turns out that in order to explain some of the more complex features, that wasn't enough. It turned out that doesn't generate enough magnetic field. So they came up with even more, and so you just want to get this idea that we have a bigger structure that's beyond that. It's a kind of a cloud, and it's not a disk. It's actually more like a donut. In fact, that's the idea. They call it a torus, and a torus of high energy plasma. High energy plasma, torus, right? What's a torus? A donut, right? A donut shape. And my drawing sucks. Look in the book. Okay? I can pull one up if you want. But it's like a big donut that goes around the accretion disk. What's the point? That makes the magnetic field even stronger, right? Okay, now if you've got that magnetic field, now you can understand why you have this. What's this? Come on, I did it over there. This. Jets. Okay, you got jets. Jets are outflow. So the AGN model has the jets. And the jets are axial. They go along the axis of the black hole. So they go in both directions along the axis. Okay? So this is like the basic model of every active galactic nuclei. We think that this is it. This explains it. As long as you got the jets, then you know there's a magnetic field. And how do you get the magnetic field? By the circulation of charged particles around the black hole. Okay? So do you have to know a lot? No, just a little tiny bit. What's the word superluminal? One more time. Appears to be going faster than the speed of light, or faster than the speed of light. Okay. All right. Blah blah blah. Oh, we're almost done. Oh, look at this. Oh, we're almost done. Congratulations. Be able to describe the nature of the Great Debate. 1920, big Great Debate. Who were the two players? Harlow Shapley and Huber. Oh, Huber, not Heber. Heber, whatever. Curtis and Shapley. Who was who? Who thought what? What did Shapley think? The Milky Way was everything. That's it. Everything is part of the Milky Way. We're all in the Milky Way. Those spiral nebula in the Milky Way, stars in the Milky Way, everything's in the Milky Way. Okay, was he right or wrong? Totally wrong. And in fact, Curtis was right. What did Curtis say? We got the stars, but all those nebula, those are galaxies in themselves. And he was right. And who proved him right? Edwin Hubble. Very good. Edwin Hubble. All right. Edwin Hubble, what was the discovery that he made? And where was it? Andromeda, Cepheid variable stars. He showed the distance was like 1,000,000 light years. In fact, the real distance is 2.5. But the idea of million versus 100,000, right? It's just too far away. It can't be in the Milky Way. All right, so we good? And he ended the debate. It was done. Everybody was like, whoa, that's really far. It must be a totally different galaxy. And then he went on to study a whole group of galaxies. And he discovered that they're all moving away from us. And that's where the Hubble Law comes from, right? The Hubble Law is that expression of how fast are they moving. And the answer is the further they are, the faster they move. How do we know that a galaxy is moving away from us? Actually, you know what? I didn't put it anywhere in the study guide, and I have a question on the final. So, how do you know that a galaxy is rotating? Right? From the red shift and the blue shift and the no shift, right? So remember the picture we drew in class, right? I don't know if we remember. We got a spiral galaxy. Okay, I got my galaxy right here. And let's make it go the other way, right? Let's make it rotate like this, right? So it's rotating like this, okay? So you tell me, I have 3 places I want to consider. I want the left-hand side, the right-hand side, and the middle side, right? What will I see in the various places? How about on the right-hand side? What will I see? You see the velocity would be coming towards us. So you see what? You see a blue shift, right? Wherever it's coming towards you, you see a blue shift. And the amount of the blue shift is exactly, you're welcome, have a good day. You see the amount of velocity of that part of the galaxy. And how about on the left-hand side? What do you see? You see a red shift, right? Red shift. Okay. Higher frequency or lower frequency?
Thank you.
Higher frequency. You're welcome. Good luck. Over here, red shift, lower frequency. In the middle, no shift, right? That's important for you to know. So how do you know the real color to consider, right? How do I know it's shifted? Well, I got to know the real color. By looking at the center of the galaxy, I know what it should be. And over here, I see something a little bit higher. Over here, a little bit lower in frequency. Bam, I know the velocities of different points along the galaxy. Okay, so I can measure the rotation curve of the galaxy. Okay. What's the difference between a spiral and an elliptical galaxy? In terms of morphology, I love that word. That was in my dissertation. Okay, who knows what morphology means? Structure, right? The structure. How is an elliptical galaxy the same? I can't think of how it's the same. Anybody? I can't either. Okay. How are they different? In what ways are they different? The shape. Okay. What's different? What's the elliptical shape? Elliptical. Okay, like a football, like an egg, right? And what's a spiral? Flat. Mostly flat, right? Pancake shape, right? A big difference right there. What else? What else is a big difference in your mind? Big difference. How old they are and their activity, right? So are they red or are they blue? Which one's red? Reddish. Ellipticals are red. Why? No new stars, right? Where do you find a lot of new stars? In the disk of a spiral galaxy, you find lots of new stars. So the colors of galaxies will shift more towards the red or blue depending on their age, right? That's actually something we don't go into too much. But we definitely know that the ellipticals are full of older stars and the spirals are full of new stars, okay? Anything else? That's probably the biggest thing. Oh, what about the numbers of, there's one more little detail, the numbers of globular clusters. Do they have the same? Pretty much the same, right? That's the wrong answer. What's the right answer? The elliptical galaxies have a lot more, right? And that makes sense because we just talked about it a few minutes ago. How do you get an elliptical galaxy? By crashing spiral galaxies together, right? And so the globular clusters of one spiral galaxy combine with the globular clusters of another, and so you get more in that object. That elliptical galaxy has more globular clusters. Okay, is it good? Makes sense? Next. All right, explain, did that? Okay, rate of star formation, new stars, where? Only in the spiral, right? Not in elliptical. Oh, how about, I got another one. Little subtle, but highly likely on your final. What can you say about H1 regions? H1 regions. What are they, by the way? H1 regions. Cold, neutral hydrogen. Yeah, you sound like me. You sound just like me. That's perfect. Cold, neutral hydrogen, right? That's perfect. And where do you find cold, neutral hydrogen? In the spiral arms, right? You don't find them at all. There's nothing in elliptical galaxies. And do you find any hot coronal gases in either one of those galaxies? Do you find that? Yeah, a little bit in spirals, but what? A lot in ellipticals, right? That's one of the, again, the indicators that it was the merger of two spiral galaxies, a very violent event. That was the way they referred to it in the book. Okay. All right. How does Hubble? Hubble tuning fork. Was he right or was he wrong?
Wrong.
Totally wrong. What did he say? Hubble. You should know what he said because that's the question on your final. He said, you don't know. Ellipticals, eggs, turn into spirals, discs, right? They first start out as eggs, and then they turn into spirals, like pancakes, right? How do you make eggs? I mean, how do you make pancakes? You got to crack some eggs in there, right? So that's what Hubble thought. But in fact, he was wrong. It turns out you got to have the pancakes first. You smash together pancakes, and you get an egg. Doesn't make any sense. Doesn't make any sense, right? I agree. But he was wrong. And we're talking about stars and galaxies right now, so that's why it doesn't quite work. We're not really talking eggs and pancakes. You like pancakes? Me too. I really do. Actually, an egg-shaped pancake would be really good right now. Okay. All right. So you guys got it? He's wrong. Spirals actually turn into ellipticals. Okay. Describe the major components. Those are the major components that I outlined for you. Right here. Okay, what's the center? Supermassive black hole. Around that, accretion disk. Around that, a torus of high energy plasma. And then we've got jets because we have that powerful magnetic field. Okay. Oh, look at this. 1/3. Actually, I forgot that. But anyway, that's kind of cool. 1/3 of the spiral galaxies. I'm not sure why I didn't know that. The rung. Should we practice real quick? What's the first rung? Stellar parallax. What's the second rung? Spectroscopic parallax. What's the third rung? Cepheid variable. Right? What's the fourth rung, which I don't like and I want to skip it? The Tully-Fisher galaxy rotation curves. What's the fifth rung? The Type 1a supernova. And the last rung, the Hubble Law. Good for you guys. You will know that. And that's definitely a question in the final, right? What's the correct order for the rungs of the astronomical cosmic distance ladder? And the current value is 69 kilometers per second per megaparsec. We don't do calculations in this class, so the only reason I want you to know that is because it's funny. That's it. Okay, that's a number that you can kind of remember. Okay, we do have time for questions. Kara's got her hand up. Anybody else? The third rung. Who knows the third rung? Help us out. Cepheid variable. Cepheid variable. Anybody else? Questions? No questions? We did it.
That was a good review.
Good job. All right, you guys did it. It's not that bad. Yay! All right, sorry we didn't get the live stream going. I'll try to upload a video. It looks like, is it still going? Oh, it's still going.